Okay, so last class we just discussed, we say we wanted to prove for central limit theorem, right? The central limit theorem is like this. Let the x1, x2, those x and each one follow some distribution, same distribution with means mu and standard deviation sigma or variance is sigma square. Then the total t, like t is a total result, x1 plus x2 plus xn will close to this normal. Mean is n mu and variance is n sigma square. Okay, so for standard deviation, take square root. So this is essentially limit theorem. So we want to prove this. So at first we simplify. We say we let yi as equal xi minus mu over sigma. Then this yi follows some distribution with mean is 0, standard deviation is 1. So we make things simple. Okay, so then for this case, so we say we wanted to prove so y1, so we see we wanted to prove this y1 plus y2 plus yn will follow this normal mean 0, but standard deviation is radical n, right? Sigma is 1. So we divide by like radical n. We want to prove this one will close to standard normal. Okay. So we say, how can we prove this? We wanted to show the moment generating function the same. We wanted to show, suppose it's t, okay? We say the moment generation function, let's say moment generating function of this t will close to moment generating function for standard normal, or standard form normal, we call this z. We wanted to prove this. So here we have the two questions. So what is standard normal's moment generating function, right? And then what is the moment generating function for t? Okay, so we have two questions. Question 1 is what is moment generating function for z of normal distribution, and we want to find what is moment generating function of t. So we find the moment generating function first. Then we can say as n goes to infinity, they are quite the same, or we can say that as n goes to infinity, the moment generating function for t and the normal, standard normal, same. Okay, so now let's check the first question. What is the moment generating function of z? So at the first we say moment generating function of x. Let's review that. moment generating function of this landing variable x is defined thus equal etx. Okay, and this can written as this equal the suppose density function is fx, so just this integration, right? Fx dx. Okay, so now what is density function for standard normal or for normal? So we say normal distribution graph just like that, right? Okay, here's 0. So what kind of functions graph like this? So a typical function is this one, e negative x squared. This function. Or let's say like we can use this fx equal e negative x squared over some coefficient, right? Over some numbers, let's say like this. So those functions, the graph just like that. Okay, so in order for this function f is a density function, we have this requirement that all probability should be 1, right? We say all probability together fx x equal 1, right? So this is the requirement of density function. Or this is just all probability adding up is 1. So for this function, maybe that do not satisfy this. This integration is not equal 1. So to make this one, so we need to multiply some constant. So how can you find the constant? So this is integration issue. But anyway, let's say for normal distribution of a standard of let's say we just say density function. We put this result first. Density function of normal distribution is thus fx equals, so suppose this normal x follow this normal, general normal, mean is mu, standard deviation sigma. So then the density function is thus, radical 2 pi sigma, then e negative x minus mu square over 2 sigma square. So why we have this coefficient? So for this one, we leave this. We will explain later on. So suppose the density function like this. Okay, so standard normal for say c, density function for z, or we not like f density function for z. So this sigma is 0. I'm sorry, mu is 0, sigma is equal 1, right? So equals this 2 pi e negative like 2x squared. Okay. So once we have this density function, we can find moment generating function. So let's say the moment generating function of z, so equals this etx and etx equals this integration negative infinity to positive infinity. Okay, and so then like tx times negative half x squared dx. So for this integration, so we at first we say, oh, we put let's say there's a coefficient we can put it inside. So this is like tx minus half x squared tx, right? So for this tx minus half x squared, we just use complete square. Let's say tx minus half x squared. So we just put this as a negative half. We just negative half x squared and minus 2tx. Alright, we just take a negative half outside. So we want to make a complete square. Okay. What's the problem? So, I'm sorry. I'm sorry. Then so my pen goes to here. Sometimes we can use mouse, but let's see. Can I erase this? Yeah, that's no. But anyway, I keep okay. So this equal negative half. So x squared minus 2tx. So we know plus t squared, right? Then let's make a complete square. So then here we minus half t squared. So that's equal negative half x minus t squared minus half t squared. Okay, so this integration we move to here. Okay, we say so equal. We take these constants outside, and so this become like negative half x minus t squared and negative half t squared dx. So for this, in this integration, t is constant. So we can take this constant outside. So this equal like e negative half negative. Oh no, I'm sorry. So here should be plus. Yeah, because this is negative, so here should plus. Yeah, plus, right? Positive t squared. Okay, so then this integration e negative half x minus t squared dx. So in this integration, t is constant, and so we just replace x minus t. We just set x minus t as the new variable as x, right? So the x from negative infinity to positive infinity. So x minus t also from negative infinity to positive infinity. So this integration have nothing to do with t. This is actually the constant. This is 1. Okay, so we find moment generating function for standard normal is this function. Okay. Okay, so now what is the moment generating function for t? Okay, so let's go back. What is t? T is this. T is y1 over n, like equal n plus y2 like this. Okay, plus yn. So what is the moment generating function for t? So according to definition, as I say, moment generating function of t equal is e t t. Yeah. Okay. So here don't got confused. This lowercase t means variable. This t is landing variable. This okay. That this t equal just equal like equal n over the y1 plus 1 over a like equal n yn. Right? This is okay. So let's say so this equal so t x equals this. X equal like equal n y1 plus like 1 over like equal n y2. Okay, and y n. So this equal this power plus this power, this plus this. So okay, so we know like a plus b equal a plus multiply b, right? So here this become, let's say, become so let's say become like t like 1 over like equal n y1 then multiply like t like equal n y2 like this, become multiplication. Okay, so this y1 y2 have no relationship, so we have this. We can say this equal thus 1 over like equal n y1 multiply t like 1 over like equal n y2 like that, t 1 over n yn. So this is y1 y2, that's y1 y2 yn, say identical, same. Okay, so the moment generating function is also the same. So this one the same. So we can write this as equal t. We put radical in here. y1 y n's power. Okay. So let's say, so what is inside? So let's say, so this is, let's say, so we have this like if like ty, this equal moment generating function of this y, right? Okay, so here we just let's say let the t over a radical n as t. So let's say, so what is the moment generating function of y? So we know this equal 1 plus mu 1 t, right, plus mu 2 over 2 t square plus mu 3 over 3 factorial t3, like that, right? Moment general function for y is this. So this is mu 1, mu 2, mu 3 is a moment of y. So we know this y mu 1 is 0. So like we say mu 1 is just y, so y equals 0. And it's standard deviation. Y's standard deviation is 1, right? So let's say standard deviation or sigma square equal 1. So what is sigma square? Sigma square equals this, like EY2. Oh no, equal EY square minus EY square. So EY2 is EY2 just mu 2, and mu 1 is 0. So you say just mu 2. So mu 2 we have mu 2 equal 1. Okay, so mu 1 equals 0, mu 2 equal 1. Okay, so here is t, we replace t by t over radical n. So we have this, so we find this one equal, so first one is 1, so plus mu 1 t is 0, plus mu 2 is 1, mu 2 is 1, so half, so t become t over radical n, so this become t square over n, right? Then plus, so here we have t3, t4, like, so we call those, so we just check t very small, so we denote this as all others compared with t2 is very small, so we use this O t square. So we can forget this smaller one, so we say this one moment just like 1 plus, almost, we can say almost equal, we just check it out, 1 plus half, so n, half n t square n. So then as n goes to infinity, this one close to will approach to which one? Okay, so here we, let's say we review this important limit. Let's say for limit issue, we say 1's infinity power, like 1 infinity so this one is undefined, so we need to check a different situation, right? So 1, so let's say for the 1 infinite limit, we have very famous this result, 1 plus 1 over n equal e. So this actually where e comes from, is this limit. So 1 plus 1 over n. So when n goes to infinity, 1 plus 1 over n is just 1, right? So this is 1's infinite power. So in little bit more general, we have this like a limit like 1. So we can say 1 plus x. So x goes to 0. So this 1 plus x is 1. So 1's infinity is 1 over x, right? So let's say 1 over x. So this limit equal e. Okay. So we can regard this formula. So then let's say, how about this one? Let's say limit x goes to, so here exact match, so not match, we just adjust a little bit. Let's say 1 plus 2x over, let's say 3 over x. So what is this limit? So this is also 1's infinite power, right? So we have to use the formula 1 plus x. So we regard this 2x as x. 1 plus this is 1 over 2x. So this is e. Okay, so this is 3 over x. So we just changing a little bit 3. So here we just multiply 6. Right? 6, yeah, becomes 3 over x. So, okay, so we can say this equals this is 6. So this limit equal e. So here e 6. Okay, so now we can go back to what is this limit? 1 plus half t square over n when n goes to infinity. So I put it to here. Okay, what is this limit? Okay, what is this limit? As n goes to infinity, so 1 plus half, so t square over n. So we just write this as 1 plus, so we just regard this as x. Okay, put this as t square to n. So 1 plus this x, so this power 2n over t square. This is e, right? 1 plus x, so 1 plus x is 1 over x power. So this is e. So this, but here this number's n's power. Okay, so we should multiply, let's say t square over 2, right? Yeah. Okay, so we say this limit equal to, inside is e, so outside is 2, so t square over 2. Okay, so we find this is just the moment generating function of z. Okay, so the moment generating function are quite close, or as n goes to infinity, this moment generating function equals, so we say as n goes to infinity, so things distribution and t's distribution the standard normal same. So we say this t well close to standard normal, and in general, so this one x1 plus x2, that those things will follow this normal. Okay, so we finish the proof for CLT. Okay. Okay, so now the other things is why the moment generating, why normal distribution density functions like this, like where does the coefficient come from? let equal 2 pi. Where does let equal 2 pi come from? So this, so let's check this problem like a suppose density function. Let's say, okay. So let's see like this question is how to derive the density function of density function of normal. So we know normal distribution basic functions if x equal e negative x squared. Like we just use simplest one. Then we just change use substitution. Like we can change x to x over 2 or x squared over like we can adjust a little bit. But the only questions are we how can find this coefficient k such that this fx we say find k, we can regard this as example. Find k such that this fx is a density function. Is a density function. So the requirement for density function is all integration is 1. So let's say like we want to find this negative infinity to positive infinity k is negative x squared dx equal 1. Okay, so how to find this k? So this means like we need this how to so this means we need to find this number, this integration. So if we find this integration, then this k is 1 over this number, right? So how can we find this integration? Okay, so we have some difficult for this one. Like if no square is negative x, easy, right? And so by the way, at the first we say this is x negative x. This is even function. So we just need to just check a positive part. So now just check this. Just check this. How can find this integration? So for this one, so for integration, we need to find antiderivative, but this one antiderivative cannot find antiderivative. So here we use some math skill. So we denote this as I. Okay, so for this integration, we just changing now the x or y doesn't matter, right? So we have this like this is also I. Let's see, negative y squared dy is also I, right? These two things same. Okay, so we multiply together, so we say I squared equal, so we can change this to double integration, like x from 0 to infinity, so y also from 0 to infinity. So this function becomes e negative x squared multiply negative y squared, so dx dy. We just changing this to double integration. So for this double integration, we can use substitution. We say this one is just the x from 0 to infinity, y is also from 0 to infinity. So this is just the first quadrant or first quadrant. So we just changing the rectangle coordinates to polar coordinate. So we just use this. We just say x like polar is we use this. This point, suppose this point xy, and this xy also can be determined by this angle theta and this length r, right? Like x equal r cosine theta, y equal r sine theta, right? So we just plug in here. So I squared, so in terms of this theta and r, so theta is from 0 to pi over 2, forced quadrant theta, right? So theta angle changing from 0 to pi over 2. And this is r from 0 to infinity. So this is for all the forced quadrant. Okay, so we just replace x and y by r theta. So this is equal e negative x squared plus y minus y squared, or negative x squared plus y squared. So we find this equal e just negative r squared. So dx dy, we find this equal, we change into d theta dr. Right, so variable change. So, and here we need to multiply this Jacobi. We said multiply, we find this r. So this is just like a double, two variable, one variable, same thing. Like let's say if one variable, maybe you're kind of familiar. Like before this dx, by now we want to change it to dt. So here we need to multiply this, right? We need a dx over dt. Use this derivative. So one variable. So two variable. So dx dy. So if we change to, let's say, change to du dv. Then here we should multiply this. X partial x over partial u, partial x, partial v. So partial y, partial u, partial y, partial v, like this. Like we need multiply this coefficient. So now if we change dx dy to du dv, we cannot simply equal. We should multiply this. So here dx dy to change to d theta dr, we find out this multiplication. We should multiply r. So here r dr. So we find this integration is easy, right? Now this is pi over 2, and for this one, this is easy because we can regard so we can use r square as a new variable. So r dr, let's say r dr equal dx dr square, right? Half. So this just become like this. If we regard the r square as a new variable, so like negative u, so du like this. Negative du, so this equal 1. Right? So finally, we find this equal, I think the coefficient is half. Yeah. So maybe just multiply. I don't know the, let's say this one multiply, so this integration half. Yeah. Okay, but it just multiply some coefficient. So then, so this is, let's say, so then, so this is for forced quadrant. So let's say for this one, actually, is we talking about all the 4 quadrant. So this we just multiply 4. So final answer just 2 pi. So like, so totally is multiply 4. Oh, the coefficient maybe I got confused. But anyway, like we have this, like r square equals this. square equals this number, then r equal, so take a square root. So this one is, let's see, maybe like this, radical pi, or radical 2 pi, maybe. Okay. So this is where radical, this radical 2 pi or radical pi come from. Okay. Okay. So today's class we prove the central limit theorem. So the idea is we want to show their moment generating function are quite close, right? So for find the moment generating function for normal, so we need to know normal distribution of density function, right? So density function, so we say normal density function is this. So where those coefficients come from? So we use this little bit this mathematical skill. Okay, and also we, as review, let's say we also check those limit, like where this limit is. So we say e equals this limit 1 plus x, x goes to 0. So here's 1 over x. So this is e. Okay. Okay. So we finish the topic for a proof for the central limit theorem. Okay. Okay. So we can stop here.